goes. Hello, everyone, and welcome back to this seminar of the numerical analysis of Galerkin ROMs series. The speaker of today is Mario Ohlberger from the University of Münster, and he will present us a talk on model reduction and learning for PDE constraint optimization. Thanks, Mario, for being here and delivering this talk. The floor is now yours.
So thanks, Francesco, and thank you on behalf of all the organizers of this seminar on model order reduction and related methods. So today I will speak about particular tools that came up in the discussion of model order reduction in the context of PDE constraint optimization. And this will involve learning in a way that we learn reduced spaces, but also in the classical sense of employing machine learning tools. So this is a collaboration with a lot of co-workers from different projects. I will hint to the different contributions also during my talk. For instance, I want to stress that a lot of these contributions are together with now postdoc former PhD student of mine, Tim Keil. And then it's a collaboration, for instance, with the group of Bernhard Haastong in Stuttgart. So Tizian Wenzel is from his group, and with Stefan Volkwein from Konstanz, where Luca Micheli and Stefan Banholzer are from his group. So let's go to the outline. I will have a small introduction and then go to PDE constraint optimization and give you the general context of so-called reduced basis trust region methods, where the major idea is that we build the reduced space and surrogate model in the outer loop of the optimization algorithm. Then I will go towards more advanced applications and discuss multi-scale problems in this context. And finally, I go to more complex problems, for instance, time-dependent problems, where also machine learning comes into this business. So let's start with some challenges which are here picked from projects where we are involved. So the first project where we develop these technologies are based on the prediction and optimization of catalytic filters. So here you see such a typical catalytic filter, and this has multiple scales. So you have this gas flow channels and porous media in between, where you have in this wash code the reaction taking place, and this can be modeled on such a pore scale. And for such large-scale computations, you want to have a really fast computation in order to be able to do like real-time simulations in the context of optimization problems. So this is a project together, for instance, with the ITWM in Kaiserslautern and a group of Bernhard Haastong in Stuttgart, and some part is from this collaboration. Another part where we are considered with large-scale optimization problem is enhanced oil recovery, and this is a project that we did together with the Norwegian Research Center in Bergen. So from there, it's the group of Lorentzen, and the PhD student involved in this project is Michael Oguntola. Here you see such an oil field with some injection wells, and for P stands for production wells, and you want to do an optimal control of this oil field in order to get as much as possible oil out of this field, and using minimal resources, thus optimizing the cost. And this is a typical mathematical benchmark problem for such oil recovery, the so-called 5-spot, where you have an injection in the middle and production wells at these 4 points in the edges. So I will come also back to this problem later, where we really have to deal with highly nonlinear large-scale systems. So I want to start with this slide on model order reduction, and the hint that in this business of reduced basis methods, there are meanwhile at least 3 standard books available where you find a lot of details on this classical approach of projection-based model order reduction. And I think that in this audience, you are aware of the classical technologies behind error estimation, then using this in a greedy algorithm to construct reduced spaces that have much smaller dimension than the high dimensional one, or alternatively to use POD methods. And when such a low dimensional space is constructed, then you project your original equation to this low dimensional space in order to come up with a reduced model. And there is also software development. There is software development in our group. Just a small advertising slide. This is PyMore, a Python package for model order reduction. This is the package that is used in all the experiments that I show you today. And the idea is that you separate the high dimensional numerical algebra or PDE solver toolboxes from the model order reduction technology. So in PyMore, only the model reduction algorithms are implemented, and there is an implemented interface to underlying solver libraries, for instance, to the Dune package, which is one where we are involved in the development, and we use this quite a bit, but also to the Phoenix or DL2 or other packages. So if you are interested, please visit the website and check out. So I come now to the major part of my talk, PDE constraint optimization. And the results that I present you here are mainly based on two papers that are meanwhile out. So one was in 2021 and the other in 22. We consider PDE constraint optimization in the following context. So we have an objective functional depending on a state and a parameter. And the state, it's itself a solution of a variational problem. So here we consider, for simplicity, first just linear elliptic problems that are behind this variational formulation. And we want to minimize this objective functional. And we always introduce also this reduced objective functional, because for any parameter you can solve for the state equation. And if you plug this map in, then you get this reduced objective functional. So what is the challenge if you want to deal with such problems? The challenge is, of course, that you want to have a very fast solution process. And in the solution process of this minimization problem, you typically imply an outer optimization solver. And this outer solver might use just the information of the state evaluations, or it might use gradient information of the objective function, or even Hessian information of the objective function, in order to have a really powerful method. And the idea is that we use model order reduction to speed up this process. And in particular, the task is that we get fast evaluation of such approximate functional gradient or Hessian evaluation. So that's what we want to do. And of course, we are not the first who tried to approach this problem. There's a whole series of papers, for instance, from the reduced basis community on PDE constraint optimizations. And in particular, maybe starting with here these works in 2015 of the group of Farhat with Matthew Saar and with Bernard Harstong. It started that algorithms were developed where the reduced spaces were built in the optimization loop. And the work where we mainly base our work here on is this work 2017 from Kian, Kreppel, Veroy, and Wilcox. I will come to this later. So before I start with these trust region optimization tools, I want to come to the general paradigm. So if you employ reduced basis in the classical fashion, then you do this offline-online splitting. And then this means that in the offline preparation phase, you build the reduced space and the reduced model. And then you are prepared. You have a very cheap surrogate model, a reduced order model ROM at hand, and you can do very fast evaluations. And if you apply this technology in the context of optimization methods, then you see if you do the optimization method directly based on your finite element solver, then you have something like the blue line here. So the objective functional approach is the correct one. And for each step here, I have some computational efforts, which is here measured in times in seconds. So it takes some time to compute forward state of the problem with a finite element solver. If you instead go from the finite element, the full order model, to a reduced order model, then you prepare offline. Now you can solve your online optimization problem very efficient and cheap. So from one step to the next step, it takes milliseconds. So it's not even that you can see the computational time in the online phase. But if you do a fair comparison of both methods, then you need to take into account also the offline time where you do this preparation. And you see that in this very simple example, the offline time is much more than the optimization method with the full order model needs to completely solve this optimization problem. And this is where we want to start and to devise methods that are able to beat also in such situations the classical technology, and this is possible by skipping the offline phase completely. So what is the idea? The idea is, and this is depicted here, we have a parameter space, and as you might see later, this can be quite high dimensional or even infinite dimensional in an optimal control problem. And classical finite element methods, classical reduced basis methods, they want to devise a surrogate model that has a given accuracy in the whole parameter space. And this is something that is not actually needed in the case of optimization problems, because in the optimization problem, we start with an initial guess, which is here denoted by mu0. This is our initial parameter guess, and we want to improve this such that we have an optimal parameter that solves the optimization problem, which is here denoted mu bar. And as you see here, what we need is just to have a good way to go this path from mu0 to mu. And this is a path which is, let's say, codimension 1 in this parameter space, independent how large this parameter space is. And this is what we want to take advantage of. And one optimization method that serves somehow as a blueprint for what we are going to do is the so-called trust region optimization approach. So what we do is we replace our overall optimization problem into optimization sub-problems. And in each outer loop, we create a surrogate model, and then we solve a minimization problem for this surrogate model as long as we can trust it. And we can trust it, this is indicated here, as long as this is the classical approach, as long as this offset where we aim for is smaller than a tolerance, which means that around such a given point where we start our optimization sub-problem, we have some radius given, and within this region we trust our model, and we can do the inner optimization loop to replace the high dimensional objective function by, let's say, a low dimensional one that is fast to compute. And if we come to the border of this trust region, then we need to enrich or to improve our surrogate model such that for the next loop we have again a method that we can trust. So this is the general picture for the trust region. And now this is the modification that we do in order to apply it in the context of surrogate models, here reduced basis methods. So what you see, what we changed is that in this point here, we do not have just that the region where we trust is such a ball around the point, which is measured here with some norm. But now we measure the quality by a relative error of the reduced model. And this can be computed by an error estimate for this reduced objective functional divided by the objective functional itself. So this is the relative error of the objective functional. And as long as this is within a bound, we can trust our method. So let's go back to this slide. So if we start here, then you see with this criteria, the trust region is this this large region here, and we can go with an inner optimization solver until we touch the boundary of this trust region. And then we enrich at this point, we get a new model and also a new relative error here, but it might be necessary that also this trust radius here, this delta K, needs to decrease. And this means that the second trust region is then this one here. And you see, when we proceed in that way, we build a reduced model that gets more accurate along the path of our optimization loop. And finally, this is the third step where the trust region has this shape. And you see that the optimum lies within this trust region, and then we can finalize the optimization loop in this third step here. So let's go to the underlying mathematics. So this was first introduced from the general idea in this work of Jan Kreppel, Villeroy, and Wilcox, and we did several modifications and improvements, and I will come to the most important one just in a minute, and this is what we call this non-conforming dual corrected approach, and you will see what this means. So first of all, if we solve these optimization problems, then we make use of the first optimized and discretized approach, which means that we use the connection between the full necessary conditions for an optimum and the corresponding definition of a dual state equation. So this is the dual state, the p mu. And this p mu allows us to have a fast access towards the gradient of the objective function with respect to the parameter. So this is why we use or need to compute not only the primal state, but also the dual state in the derivatives of the primal and the dual state with respect to the parameters. And they also solve PDEs, which are given in this line and in this line. So just as a reminder that now it's not just the task to solve for one equation, but for a whole set or system of equations in order to do this optimization task. So if it comes to the reduced objective functional, so this is what we had before on the finite element level, this was this one, and we now want to have the same construction now on the level of the reduced basis method, and this is what we denote here by Jn hat, then we see that we need to do a correction here, because different from the finite element method, the spaces that we construct to approximate a primal solution, UN, and a dual solution, PN, they do not coincide. And this is somehow a variational crime, because then you cannot use the solution of the dual problem as a test function in the primal problem. So this residual is not zero anymore, but it has some value. And you need to consider this as a correction in the reduced functional. And then, of course, you want to solve this minimization problem. And if you do this correction appropriately, then you can do all the a posteriori error estimation accordingly. And this is what is now shown here. So the first one is the a posteriori error estimate that you get for the objective functional itself. And this is the reduced basis objective functional compared with the high order, full order model objective functional. And you see that here now you have perfectly these quadratic terms. So this is the a posteriori error estimate of the primal equation. This is an evaluation of the dual residual. And here you have the a posteriori error estimate of the primal squared. And the same holds true if you go towards the gradient of the objective functional, then you can also derive, it's a quite lengthy calculation, such optimal a posteriori error estimate, and they are all in the fashion that we are used to in reduced basis methods, which means that they can be efficiently offline, online decomposed. Okay, with that, I see there are some problems in the slides here. We can also formulate a rigorous result that the optimization algorithm that we define in that way. And you see, this is the definition of this trust region optimization subproblems, which are error aware. So the error estimator steers the region where we trust our method. And then we have a certain criteria which terminate the inner optimization loop. And the overall algorithm then actually converges to a first order critical point of this constraint optimization problem. And as this is a constraint optimization problem with box constraints, we have this projection operator to the box constraints here in the formulation. So everything fine, and we have a full theory for that. And I can come to some numerical experiments. And this first numerical experiment here gives an optimization problem, which is based on the floor map of the building where I'm usually working in. So this is our mathematics cluster in Münster, and we have a big common room. And we want to save this optimization problem in such a way that we get an optimal temperature distribution in this childcare room. And the parameters in the system are, for instance, the strength of the heatings, which are below the windows, and all the wall and window materials, which means that we can adjust the diffusion or the heat conductivity of these materials. So what you see here, this is the heat conductivity of the materials. This is visualized one of the heaters, one source on. If this source is on, then the primary solution looks like that. And this is the dual solution, where the dual solution is with respect to getting this temperature in the childcare room fixed. And if you now compare the solution strategies that come out of this algorithm with what I've shown you at the beginning, where we have this large offline phase, and then certainly the model reduction pays off. In this case, you again have as a reference this red line. This is the convergence of the full order model solver. So just taking optimization, and for the state equations and dual equations, you just use your finite element solver. And the methods that are here, these are the different variants that we propose. And they differ, or they are a little bit faster than the method which you see in light blue, which is the original suggestion of this in this paper of Kian, Kreppel, Veroy, and Wilcox. So you see the method typically behaves in the following way. At the beginning, we follow more or less the full order method until the basis that we construct by just exploiting the parameter space in these points to enrich our reduced basis space is good enough. And then certainly it takes off, and we get this very fast convergence, which is similar to the online phase in this offline-online splitting behavior. And the difference that we see here between our approaches and the approaches that you find in this paper, they come from this correction in the reduced objective functional and the optimal a posteriori error estimates, which gives us this speed up in the method. So this is the general idea. You have the outer optimization loop, you collect information, and you use this information to get a speed up of the method. And therefore, these reduced basis methods are here not employed to approximate the whole parameter regime, but just to help to find the optimal parameter in even a large parameter domain. Okay, I come to the next part of my talk, which is now for multi-scale problems. And you can imagine if you go to multi-scale problems, then already your full order model might be a problem if you go just with standard finite element type models. So the bottleneck for large problems, global FEM solves become infeasible, and we need to do some localization in order to deal with such large scale problems. And here we want to look at these problems in the typical multi-scale context, which means that the underlying problem is supposed to have very heterogeneous diffusion fields. So in this context, related to model order reduction, there is a huge activity on different methods that can be used, forward problems. So here, for instance, I refer to the reduced basis element, to the port-reduced methods, but also hybrid methods. And in what we are going to do now, for instance, hint to these methods which are called reduced basis LOD, where LOD stands for localized orthogonal decomposition. This is a particular full order multi-scale method that we will address also in this talk. And we have a recent review where we also sketch how these zoo of methods can be brought into an abstract framework. So let me go and start with a general idea. So we have a global solution space. This is your finite element space, and we want to localize, which means that we want to decompose into local spaces VI, where these VIs are somehow compactly supported in some area omega I, which is compact in omega. If this is the case, then the reduced spaces cannot directly be or should not directly be constructed for the global space, but for the local components. So if we have a reduced local space, which means this is a subspace of these local components with some dimension Ni, then we can again, in this method, come back to a global space by just using this direct sum. And of course, the overall dimension is then just the sum of the local dimensions. So this is the general idea, and the methods differ in how we split this global space into local ones. And one of these splittings I will discuss in a minute. So if we have this decomposition, then of course the reduced method is nothing else than a Galerkian projection of your original variational problem into this space with the decomposition that you have here. And there are a lot of ideas that you can then use. They are from multi-scale methods, from domain decomposition, also ideas like localized training or adaptive enrichment. All this comes together in this framework here. So let's go to this local orthogonal decomposition method, which was introduced by Malmquist and Petersheim in 2014. So the idea here is that you have a fine scale mesh, and you decompose into a coarse mesh and some fine scale part, which in the end should be somehow orthogonal to the function space on the coarse mesh. And this is done in the following way. First, you have a coarse scale interpolation operator, which acts from the finite element space on the fine mesh to the finite element space on the coarse mesh. This can be an L2 projection or any other interpolation operator. With this, we are able to define a fine scale space, which is just the kernel of this interpolation operator. So everything that is mapped to 0 by this interpolation operator is in this fine scale correction space, VF. And of course, this gives us a decomposition of our original function space into the coarse and the fine component. And this is visualized here. So this is some finite element function on a fine mesh, and you decompose to the contribution on the coarse mesh and the fluctuations. And the idea now is that you do not take this decomposition as shown here, but you want to have a second step such that this decomposition gets orthogonal with respect to the bilinear form that you are looking at. So what you are really aiming at is that you get a decomposition which is an orthogonal decomposition between a multi-scale space and a fine scale space. And in order to achieve this, the coarse scale finite element space needs to be corrected by this correction in order to get this multi-scale space, which is orthogonal. And this correction is given by the solution of this problem here in the fine scale correction space. And here's now, of course, a problem because this fine scale correction space has more or less the same dimension as the original finite element space, such that the construction here needs these solutions, and you do not really save complexity. And in addition, as the bilinear form here is mu dependent, this has to be done whenever a new parameter is picked. And this calls the usage of the reduced basis method, for instance. But in order to make this efficient, you need this localized orthogonal decomposition. And I now talk about localization. And this is done in the following way. So we have, again, this problem here where you solve for these corrector functions. And this problem is now not on the whole fine scale correction space, but only on the fine scale correction space in certain neighborhood of a coarse scale element. And this can be done due to this lemma, which was proven in this paper of Malmquist and Petersheim, that by truncating the global problem for the correctors to the local ones, you have exponential convergence with respect to the layers that you take here. So if you compute this with 2 layers, then the error due to exponential decay is already so small that you can work with this truncated localized correction problems. And this means that we now can define this multi-scale space, and again, we solve these correction problems on the localized domain, so on this neighborhood of T, and this is done using reduced basic technology. Okay, completing our full order model is now a Petrov-Galerkin local orthogonalized decomposition formulation like that. And we want to speed up this method here with reduced basis methods. And this was actually done in a work by Tim Keil and Stefan Rafe, which is on arXiv, and it will be shortly published in ZISC this year. And there a full reduced basis method is proposed to reduce this local orthogonal decomposition method and get full speed up. So in what I present here, and this is from this work with Tim Keil, which is also on arXiv, we want to use now as a full order model in the optimization problem, this Petrov-Galerkin LOD, and as a multi-scale reduced order model, the corresponding 2-scale reduced basis method that approximates the Petrov-Galerkin LOD. So I don't go into the details of this method. If you're interested, please check. So we bring now all this technology together with the trust region approach that I showed you before. And we apply this now to model problems where the underlying structure has such multi-scale features. As you see here, this is a thermal block problem that we pose in such an optimization framework. And the underlying blocks here have conductivities with heterogeneous fine scale structure. And it's it's a cooked up model problem where you have, let's say, this fine structure on 2 different scales, and each block is then a linear combination of conductivities of this scale and of the scale here. So overall, this is a 4x4 thermal block, which each block has these 2 different possibilities of base functions, and this means that the parameter domain here is 32. So it's already quite high dimensional, and of course we expect that the trust region method pays off in such high dimensional cases. And this is what you see here. So this is the resolution that you see here is the resolution of the coarse mesh. And you see that the coarse mesh blocks are already quite fine. And in the ideal case concerning complexity, the number of coarse scale elements should be the same as the number of fine scale elements that you have in each local subproblem solve in order to do this local orthogonal decomposition construction. So the underlying fine scale mesh here has about 16 million degrees of freedom, which is not feasible anymore for direct finite element solvers, at least if you do not spend really highly efficient methods on parallel machines. And the number of coarse mesh elements in this case is about 1,600. so what you see down here is that if you solve the overall optimization problem, and then with finite element and this global trust region reduced basis method, we were not even able to solve these problems because just one global solve is too expensive to do that. But with the Petrov-Galerkin LOD, you can do this directly in this trust region context, and you see the simulation time here. And if you now employ this additional speed up with the two-scale reduced basis method and also some tricks to speed up the trust region optimization solver. This is the relaxed version with the R here. Then you see what you benefit and how you can bring down this computation time to some reasonable time for these large scale problems. So far we dealt with problems with increasing complexity from, let's say, moderately large-scale problems to really large-scale multi-scale problems. But still, we are with very simple elliptic problems and also with stationary problems. And in the next part, I want to go towards parabolic problems and to give you somehow some ideas how we can also profit and speed up the methods for parabolic problems, and this is by using also machine learning ingredients in a way as it also has been introduced before in several other contributions. I will come to that. So we look now at parabolic problems, and in the end we want to solve optimization or optimal control problems with these parabolic state equations. So this is always kept in mind, and the technology that we had so far with the reduced basis method certainly gives a good compression in space, but so far we need to do the same time stepping schemes as for the full order models, and this is the major bottleneck here in order to further improve the speed of the solution for time-dependent problems. So this means employing the technology that is already available, we can construct a reduced space with a small number of basis functions, and then the solution, which is now time-dependent, can be expanded in the basis that we constructed with the reduced basis method, either with greedy or POD greedy or POD. And the coefficients here, they are of course then simulated by projecting into the reduced space. And if you do this with classical reduced order models, then this leads to a time stepping scheme to compute these coefficients here. And this is where now we want to employ machine learning in order to directly compute these coefficients by a machine learning model instead of Galerkin projection, and thereby avoiding the time stepping procedure. And we have two variants how we do that. So we have a vectorize and a random access variant. So you want to train a machine learning model. This can be a neural network, but in our case, we also very successfully used kernel methods developed in the group of Bernard Harstrong, the VCOGA. So we want to train to get such a map that maps from the parameter space to the whole trajectory of these coefficients in time. So the parameter is mapped to the whole trajectory in time of these coefficient vectors at once. So this means whenever you have trained this network, then just plugging in the parameter, you get the whole coefficient for the trajectory, and you immediately have the whole time-dependent solution. And the other variant is the random access in time, where we train a map that not maps from the parameter to the whole trajectory, but from the parameter and time. So time is here in the same function as the parameter itself to the corresponding coefficient here for this parameter at this time point. And this means if we have such a map, then we have a random access to the solution in time. So we can get the solution at time point 10,000 without doing a time stepping scheme until this point. So this is the benefit that you can get. And as this all fits into the framework of the approximation in the reduced space, so we always have the ROM at hand, we denote the coefficients that we derive in this way as UML, so the machine learning model. Unfortunately, I see that in my slide, this is not here. So what we have now is we have a hierarchy of 3 models. So we have the full order model, which is the full finite element model for the parabolic problem, which is very accurate, but also very slow. We have the reduced order model, the ROM, by classical Galerkin projection and doing a time stepping in a reduced space. It's faster than the full order model. It has a rigorous certification with error estimation, but of course you have this low iterative time stepping. And this goes away if we use this machine learning model instead, where you have this very fast evaluation for all time instances. But so far, this is not certified. And here is one of our major contributions, which is a very simple idea, as this machine learning model is just other way of computing the coefficients in the reduced spaces. Then it's completely clear that we can use the certification and a posteriori error estimates from reduced spaces methods also for the machine learning model. So for these time-dependent problems, we already know since quite some years that we have this optimal a posteriori error estimate where you get the sum on the time steps with the residual in the case time step in the dual norm here. And you just need to plug in here your reduced solution. And this reduced solution can now be just replaced by the machine learning solution because this lives in the same space as the reduced spaces solution. In that way, the error estimator can be used also for the machine learning model. And then we come up with such a model hierarchy and let's say a black box solver that builds the machine learning and the reduced order model on the fly in an outer optimization loop or in an outer process that is defined in any other way. This can be also uncertainty quantification or other scenarios. So whenever a new parameter comes into this black box, and then the goal is that you give back the solution of the parabolic PDE for this parameter as fast as possible. So if you start with this procedure and your machine learning model or your reduced spaces model is not trained well enough, then what you do is first, of course, you have the model that is already in the black box. It can be empty. It can be any preparation step. So you compute the error estimator that is now available. And if the machine learning model is good enough, then you just return the solution with this machine learning surrogate model. If it's not good enough, then you compute the next higher order level, which means the reduced order model. You compute the error estimate also here. And if this is good enough, you return that one. If this is not good enough, of course, you need to go to the full order model. And whenever you touch a model that is more accurate in this hierarchy, then you need to compute the solutions here. And this means this generates training data for the next faster level. So if you compute reduced order model solutions, then you collect training data, and this is used to improve the machine learning model for the next evaluations. And in the same way, if you call the full order model, then you collect training data from that, and this is used to improve the reduced basis method. And in that way, it's an on the fly construction of this model hierarchy. And you can see this model hierarchy now just as an optimal black box solver for your problem that gives you the desired accuracy solution with minimal effort. And this is now used in a problem that is related to these catalytic filter problems. So you have here this flow in a channel and then reaction in this wash code. You minimize an output functional, which measures how much pollutant you have in the outflow here. And the parameters in this experiment are the physical parameters, the Peckley number, so the impact of the speed of the velocity, and the Damm-Kühler number is the strength of the reaction term. So for this problem, we applied now our strategy in order to minimize the pollutant that flows out of this device. And what you should first of all see is this plot down here, where you see the number of calls for your state equation in order to solve this optimization problem, and the runtime that is used to get a solution for a particular parameter. So this means this is in the parameter space. You pick a certain parameter, and then you call this black box solution hierarchy, and the solution hierarchy now checks whether you need really a form solution, or whether the reduced basis solution is good enough, or the machine learning is good enough. And the blue bars here, this is whenever the algorithm decides that you need a full order model evaluation because the other two models are not good enough. And you see that in this whole optimization problems, there are only 5 or even 4, 1, 2, 3, 4 calls of the full order model in order to solve this whole optimization problem. And with this information, then a reduced basis, the ROM is built. So the reduced basis method, these are the yellow bars here. So they take far less runtime, and this is in logarithmic scale, the runtime. And you see that now these reduced basis method is used at the beginning a little bit more, and also after new information came in a little bit more. And from that, data is collected to improve the machine learning model. And you see that in most of the calls, it's just enough, this is the green bars here, to compute the machine learning model in order to solve this overall problem. So also in this example, you see that we use learning, in this case, combined training of the reduced order space and training of the machine learning in order to get an optimal speed up in such optimization problems. Finally, I want to come to the last part, where now we solve these very complex problems of enhanced oil recovery. And in this case, the problem is so complex with nonlinearities and systems of black oil recovery that no a posteriori error estimate is even there. And also the solvers become so difficult that we skip completely the reduced order model and just go with machine learning acceleration. So in that case, we maximize the benefit, which is the net product value function here. So this is defined in a way that it shows the price in US dollar that you gain by exploiting this oil field. And this means that if the oil production is high, then this adds to the objective functional. And if the costs that are, for instance, by injecting water and polymers are high, then this is with a minus sign in the contribution. So all these are minus contributions where you need to pay for. So the underlying state equation here is a black oil model where we add a chemical component. So it's a oil, water, and gas phase, 3 phases, and 4 components model with highly nonlinear structure. And this is known to be a degenerate parabolic system. And currently, there is no hope to get a rigorous a posteriori error estimate for these kind of problems. And we need to get other methods of certification if we want to use machine learning models here. So what we do here is we employ machine learning in a different way than I told you before. And we have also here 2 approaches, a scalar valued and a vector valued one. In the first one, we train a map that directly maps our control parameters to the objective functional, the overall objective functional. So the map is from the number of control parameters to this real value of the objective function. And the vector valued case, we make use of the particular structure of the objective functional. It's a scalar product of such a weighting vector with these contributions of the different ingredients of this objective functional. And we first construct now a neural network that maps on the vector of these different contributions, and the overall objective functional is then obtained by this scalar product here. Okay, and in the same way as before, we have now an outer inner loop optimization algorithm, which means in this case, we cannot use this machinery of dual problems and using dual problems to compute gradients of the objective functional, but we only have access to the state equation and to the objective functional evaluated for the state equation. So in order to compute a gradient in parameter space, at some point, this method uses an ensemble optimization method, which means it draws randomly in this area, locally, like 10 to 40 random parameters. It computes the solution in these random parameters, and from these solutions, it computes a gradient. And then this gradient is used in order to do the optimization and come to the next point. And what we do here, so this would be the classical optimization loop, where in each of these points, you call in each point like 10 or 40 times the underlying full order model, and then you compute the gradient, and then you do the next step. And instead, we compute with a full order model one gradient, and this already involves a number of full order model solves, and they are used to train the neural network that does this mapping from parameter to the goal, to the objective function directly. And now we have a surrogate at hand, and we use this surrogate in an internal inner loop of the optimization solver to come to some other point where this local surrogate model already is in its optimum, but it's not accurate. At that point, we again go back to the full order model and check for the gradient of the full order model. And this gives us a possibility to certify whether we are already here in a local minimum, or if the gradient is already close to zero or not. If not, then we take these evaluations, we improve by a retraining our machine learning model, and we do another inner iteration with the improved machine learning model. And what you see here is that in that way, we can enormously speed up and improve these optimization problems for such large scale oil recovery experiments. So this is the value function here. You see, we want to maximize in US dollars the outcome of this exploitation of oil fields. And this is what we get from the optimization if we just use our full order model in this ensemble optimization solver. And you see at some point you arrive at this local optimum. And if you now go with the suggested machine learning models, and here you see the scalar version on this side and the vector valued version here, then you see that you take a much faster path. So within a few outer iterations, you are already done. It's much faster. And at the same time, we see that we arrive at a different local optimum. So this machine learning model at the same time serves as a kind of regularizer for the underlying problem. And you converge into different local maxima. And actually, these are local maxima, and this is done by checking the gradient with the full order model. And you see that on this way, this is the difference between this orange curve and the red one with this dots here. These are the evaluation of the machine learning objective functional. And if at the same point we evaluate the full order model, then you see there is an error, but in the progress where we enrich and retrain our machine learning, both curves come together. And in the end, when we certify with the full order model that the optimization problem is solved, that we are in a local optimum, then of course the machine learning and the full order model are in this point actually giving the same answer. So with this, I'm at the end of the talk. This is just to show you how this optimal control then differs in oil production, water production, and polymer production. Here you see here that in oil production, the new machine learning models give a much higher exploitation of oil than was obtained with this optimal solution just using the full order model. And in the other components, water production and polymer production, which is a cost in this case, the full order model gave much higher rates than the machine learning model. And this is why in the end, it's not only a speed up of the method, but we actually find also other local maxima that are much better than those that were found with the full order model. Okay, and also in absolute speed up, you see the speed up in CPU time with respect to the full order model here. So with that, I'm at the end of my talk. I thank all my co-workers, and what I want you to take home from this talk is that in problems like optimization problems, you do not need a surrogate model that is accurate in the whole parameter space, but you just need it tailored towards the optimization problem, which means to find the right path and a good approximation around the optimal solution. And this makes it possible to go from the classical offline-online enrichment strategies to online enrichment, online learning strategies. And this is both for classical construction of reduced spaces, but also for construction of machine learning models. Thanks.
Thank you, Mario, for your presentation. And now we have a few minutes for questions. So now the floor is open for attendees in case they have questions. So if you have a question, just feel free to open your mic. So I think that Ryan has one. So Ryan, go ahead.
As always, thank you, Mario. This was a very nice presentation. Thank you. I have a generic question. So when you talked about the, I think this was on slide 17. You're talking about how you have to choose different test spaces and trial spaces, I believe. Yeah, right. So if I understood correctly, you're saying that you have to the dual information is not included in the basis, and then you have to use this correction term, which I thought was very interesting.
Yeah, so we tried different combinations. You can also construct the same reduced space for the primal and dual. So just by taking double the number of base functions.
Yeah.
And of course you can do that. This is also what we checked, but this method does not perform as well as the one that we propose here. And of course, if you go that way, then of course you would be in a situation that this is 0 and you can go with the other error estimate. And we checked also a third variant, which is you can also go for Petrov-Galerkin approximation, where you do different primal and dual spaces, but you do the primal and the dual in a Petrov-Galerkin with different test space than ansatz space, then also you get rid of this term. But also there we found that it does not perform better than the one where you really tailor and get full benefit of the small dimension of both components.
Okay, very nice, very nice.
But this is an immediate question, right?
I know. Okay, I have other questions, but maybe I'll wait until the other people ask. So thank you.
Okay, let's see if there are other people that ask. Maza, please go ahead. Hi,
Mario. I really enjoyed your talk. Actually, related to Trian's question, if you could go to slide 23, there are a number of curves on this slide, I think. 23, sorry.
Yeah.
Is the one that says 1B where it says primals equal to dual. How do you construct that space? The 1B.
Yeah,
That
that
one.
one.
Is that the one that includes both snapshots in a given
Yeah,
space?
we include both snapshots. Yeah, this is the larger space, right?
Okay. Okay. That makes sense. Another question I had is that when you solve this trust region sub problem, do you solve it exactly as a constraint optimization problem and traverse along the boundary, or do you quit as soon as you hit kind of the
Yeah, this is also, yeah, this is a good question. So this is different from classical trust region. So we quit as soon as we touch the boundary.
Okay, okay.
Yeah, and this is because here the trust region, this error-aware trust region is different from the trust region that just bounds the area with a norm. So as soon as we touch the boundary, we stop, and then we go to the next one.
Okay, thank you.
Yes, Trajan, yes.
Okay, so now my turn. So on slide 29, right. This was very interesting to me. This was really, so I didn't actually, so the localized orthogonal decomposition. So this decomposition sounds very much in the same spirit as variational multi-scale methods that Tom Hughes and the others have pioneered 2 decades ago. And
yeah, of course, this is quite related, yes. So the
okay.
difference is actually this construction where you get this orthogonality with respect to the bilinear form. So
right. And I saw that, and I think that that's very interesting. And I was wondering, I think that Ramon Codina has looked at the orthogonal subscales that's in the context of variational multi-scale methods, and I was wondering whether there's any connection between this idea in Malquist and Peter Simon and Ramon.
I don't know this work actually, but at the same time, Omadi was working on operator approximation, and this can be mapped. So the local orthogonal decomposition can be mapped to these works of Omadi in operator approximation.
Okay. Well, I mean, anyway, so this was very nice. I really appreciate this line of work. I think that this is very, very good, a very interesting idea. So thank you.
Thanks.
Okay, so Thomas.
Thank you, Francesco. Hi, Mario. Thank you very much for this very nice talk. Really interesting. So my question is also related to Trajan's one. It's about the decay of this or localized orthogonal decomposition. You mentioned that it decays in an exponential rate, and that the velocity, let's say, depends on the number of layers of overlapping, no?
Yes. So if you increase this overlapping layers, then you get exponential decay of the error.
Okay. So my question is, does the decay also depend on the strength of the coerciveness or coercivity of the form?
Yeah. So
that if instead of let's say a symmetric elliptic operator, you have something like a convection diffusion one.
So this is also written here in the statement of the lemma. So the contrast enters into this constant here. So it's not in the exponential rate, but it might be that this is a quite large constant if you have large contrast. And there are actually also works where they try to work on getting rid of this bad dependence on the contrast here. And these works, they introduce particular interpolation operators that are robust with respect to the contrast, because this is all related, these constants here are all related to the stability estimate for the interpolation operator that you use.
Okay.
So as soon as, so go back, this interpolation operator here, as soon as you have an interpolation operator where the stability is robust with respect to contrast, then this transfers also to this approximation result.
Okay.
But this is hard work. So, for instance, there are some situations where you have just a fine structure like black-white, so a high value and low value, high contrast. And then these interpolation operators actually need to interpolate only within one of the regions in order to get this stability. So there is an article of Malquist with co-workers where they introduce such a stable interpolation operator for a very restricted regime.
Okay, okay. It's very, very interesting. Thank you very much, Mario.
Thanks.
So I think Masa has another question. Is that right?
Yeah, sorry. Yeah.
Yep.
So on your work with the machine learning model with the reduced basis error bound, how does the cost of evaluating the solution and the error bound compare for like typical cases?
Yeah. So this is, we use this a posteriori error estimate also for the machine learning. And the first point, this is a good point. If you want to use really this certification, then you need the whole trajectory also with the machine learning model in order to be able to evaluate this error estimator. This is the first point, because I showed you this this version with the random access. This does not pay off too much if you want to use the error estimate, because you need the whole coefficients in time anyway. And the second step is certainly that for the evaluation, you need to make use of offline-online decomposition in order to have fast evaluation of the error estimate. But in general, and this is what you see here, these are the CPU times that include this evaluation of the a posteriori error estimator. And this means that, so you see here that also the machine learning model is not really that cheap. And this is just because also the a posteriori error estimate is evaluated, but nevertheless, you just need to evaluate the error estimate, and you do not need to do the time stepping scheme.
Yeah.
And this difference in CPU time, this is what you see here in the difference between the reduced order model and the machine learning model.
That makes sense. Thank you.
Yeah.
Okay, so let's see if there are further questions from the audience. Okay, so if not, I would like to thank Mario again for his presentation. I would like to thank every one of you for this very nice discussion that we had after the presentation. So thanks again, Mario, and we'll see you next week on Tuesday at the same time. Bye.
Thanks, Francesco. Thank you.